result. Yes.
And for this particular case, you could just make sure that you find the bug that you just fixed. So in the previous slide, we just fixed the bug. If you just want to, we should just add the line to this exercise that says, make sure you can find the bug we just fixed. So if you test the faulty version, your return a single binary tree all the time, you'll never find the bug unless you handcraft that specific counterexample.
Right. In general, so a meta comment is some of these questions are about kind of adversarial uses of the framework that we have here. And of course, random testing is not a very good way to find adversarial bugs. So if the bug has the form, if x equals 537, then do something bad, else behave normally, your chances of finding that by random testing are slim. So the assumption here is that the tester is friends with the system designer.
How difficult is the completeness theorem you talked about?
How difficult is that completeness theorem, Leo?
It's a Popple paper.
It's a Popple paper, so Popple 18.
So is the next step fuzz testing or something like that?
Is the next step fuzz testing? I would say this is a step beyond fuzz testing as I understand the term. So when people usually talk about fuzz testing in the testing community, it's used where the property is basically program doesn't fall over with a runtime error. So that's a property that you can write down in a quick check-like system, but there are many more interesting properties that you can also write down.
But maybe I meant white box fuzz testing.
So you mean white box fuzz testing? So yes. So in the testing community, there are many more sophisticated ways of producing test cases that don't just rely, for example, on code coverage. But that try to explore the execution space of the program and sort of interactively generate the tests to try to drive the program into interesting regions of its state space. That is something that we have not yet explored in the Quick Check framework and totally should and intend to. So as I commented a couple of times, testing is a gigantic area. There's a lot of good ideas that in many cases could be applied here.
We've seen some size generators, and shrinkers are basically the opposite of a generator. Couldn't you use kind of the size of the generator to generate smaller tests? So if you have a large failing one, reduce the size and generate a new one, and thus avoid having...
So that's a good idea. So the question is, couldn't you use your size generator instead of a shrinker, or use it as a shrinker by just observing the size of the thing and then generating things a little bit smaller until you find another counterexample? That would work fine as long as the sizes are fairly small. But if the size of the original counterexample is huge, then generating all things one step smaller, or generating lots and lots of random things one step smaller, would take a long time. And so why, that leads to another question. Why would you want to generate huge examples? It's really interesting. Huge examples tend to be, in many domains, much more effective at finding bugs. And the way to think about it is this. Suppose you're generating random, say, machine code programs. If you generate a large random machine code program, and now suppose that your property is falsified by certain instruction sequences. So you need to have 2 pushes followed by an add. A long program is going to have a pretty good chance of having a subsequence of its instructions that look like push, push, add. In some cases, there will be things between the pushes and the add that make it not an interesting test, like there's a pop or whatever else. But in many cases, if you take a an actual counterexample and interleave it with arbitrary random stuff, it will still be a counterexample. And from that observation, it follows that large test inputs will have not just a little bit higher chance, but an exponentially higher chance of tickling bugs, because they have lots and lots of subsequences. So experience in the quick check community shows that it's better to generate counterexamples kind of as big as you can and then shrink them down, at least in many situations. And let me make one more comment. Since we're after hours, I will restrict myself to one more comment, which is, you've heard me say many times in this lecture, in some situations, or here's what you might like to do to understand what's going on in your domain. And this should suggest to you that random testing is not a push-button matter. Very often, for very simple properties or very small artifacts, you can get away with just writing down the simplest thing and deriving your generators automatically and pushing the button and you get a counterexample. And that's a good way to start. But it doesn't get you all that far. So it's nice to have automatic generation of things because it gets you going. But you should recognize that it really is an art, and you need to develop some expertise in driving these tools in order to get good results out of them. On the other hand, I can also tell you that developing that expertise is not all that hard, and people that are good at random testing are quite effective at discovering bugs.